Hello my dear student, myself Sanjay Sharma. I am again here with my another module of class 12th physics electrostatics and the module is 8. Now the today's topic is application of Gauss theorem. So today we will start first application of Gauss theorem, that is electric field intensity due to an infinitely long straight wire. The question arises, how can we apply Gauss theorem? In our previous module, I already told you that whenever we want to apply Gauss theorem, firstly we have to consider a Gaussian surface. What is the Gaussian surface? I am just reminding you again. Gaussian surface is the symmetrical shape closed boundary around any charged particle. If any charged particle we have, and we are just bounded it in a closed boundary which is having the symmetrical shape, that will act as a Gaussian surface. It is the imaginary closed surface. It is not lying practically, but we will consider it as it is lying here. So as the topic is infinitely long straight wire, so as I have taken here, this is straight wire. So just consider this is an infinitely long straight wire which is having the length up to infinite, but the area of cross section is negligible. Mean we will pay attention on its length only. We have considered already that the area of cross section is equals to negligible. I am not saying 0, but it is negligible. So if we want to find out electric field intensity at this point maybe, or at this point maybe, so firstly we have to consider the symmetrical shape closed boundary around this wire. Charge is present on this wire on this length only. I have already told you the area of cross section is approximately 0, you can say negligible. So the charge is not present at this surface, at this portion. So when we will consider a closed symmetrical shape boundary, then you can understand about it. The closed symmetrical shape boundary is just like this, because electric field may be lying here because charge is present here. If charge is present here, electric field may be lying here. Electric field lying here, electric field lying here. If we take the equal distance and we just make the equal distance in a complete manner, then you can understand what kind of shape of the Gaussian surface, and that I am telling you in this manner with the help of this hollow pipe. See, if this is a wire, then this pipe is behaving as the Gaussian surface. So here, this pipe is behaving as a Gaussian surface, then you can understand that what kind of Gaussian surface takes place in this situation. Now, the first step is to consider the Gaussian surface around the charged particle. First step we have done. Now the second step is, see how many surfaces are there. So you can see first surface is here. This is the first surface, and this is the another surface, and this is the another surface. How I have said that? Because if we have surface, then it has some surface area also. So the shape, or you can say the face of the surface is now towards you. So what is the direction of the area vector of the surface? Just like this. If I am considering the elementary portion here, then where the direction of the area vector now? Just upward. And at the back side you can see, this is the face of this area. If this is the face of the area, then where the direction of the area vector? Here. So here you can see 3 different directions of area vectors are present and on the 3 different surfaces. So here the first surface is this, the second surface is curved surface, and the third one is this surface. So these are the 3 different direction of area vectors which are having different 3 surfaces. Now see on the board. Let's say this is our infinitely long straight wire, and the charge is present on its surface, charge is present on its surface. I already told you that charge is present on its surface only, not on the area of cross section. So, if we want to find the electric field at this point P, then you all know that if the charge is present, then this is the direction of electric field intensity. This is the direction of electric field intensity, beta. Now, if these distances are, you consider a symmetrical shape of closed boundary which is having r distance from this wire. So that kind of shape I already discussed, that is having cylindrical shape. So in this manner we have to make a Gaussian surface, and it is just like this. This is its first surface, this curved surface is the second surface, and this is its third surface. I can mention here first surface, second surface, and this is the third surface. You can make it dark also. You can make it dark also. This is the Gaussian surface which we have considered here. Now, at point P, we want to find out electric field intensity. For that, we know what we have to do. Simply, we have to find electric flux. And then we will apply Gauss theorem. So, firstly, I will tell you what is electric flux. I am telling you, or you can say I am reminding you the definition of electric flux. The total number of electric line of forces passing through a unit area held perpendicular through that surface is called as electric flux. So how many faces are there? We have find it 1, 2, 3. There are 3 surfaces. So we will try to find how many surfaces of this Gaussian surface are contributing an electric flux. And then we will apply Gauss theorem. What is Gauss theorem, beta? Just remind it. The total electric flux over any closed surface in vacuum is always 1 upon epsilon naught times the total charge present inside that surface. See, firstly, we will try to find the electric flux over the closed surface, you can say Gaussian surface. And then we can write closed integral of E dot ds. But here we have put the closed sign, but now we have to split this closed sign into 3 different parts. Why? Because if you consider small elementary area here, then this is the direction of area vector. If you will consider small area here, then this is the direction of area vector. If you will consider small area here, then this is the direction of area vector. So here 3 surfaces are there, and on the 3 surfaces the area vector direction is also different. So we have to split this complete closed integral into 3 different parts. Now we have to see what the angle made by electric field at the surface. So electric field was upward as we have taken. So electric field is here. Electric field I have already shown here. This is electric field. This is area vector. So angle here equals to 0. And here angle equals to 90. And again, if we want to find out the direction of electric field, then we all know that this is the direction of electric field. Angle is how much? 90 degree. Again, try to find it. Area vector in this direction. Electric field we have shown already. This is in upward direction. So what is the angle between electric field and area vector? 90 degree. Here electric field in upward direction. Area vector direction is also upward. So angle equals to 0 degree. Here the direction of area vector. Here electric field upward. Angle is 90 degree. So when we will write again, we can write without close sign E dot ds. This is for the first surface, and then E dot ds. This is for second surface, and then E ds. This is for third surface. This is the total electric flux. Now we have to see the role of angle. See here, if we want to find out electric flux, then we have to open the dot product, and then we can write E ds cos first surface angle is 90. So here we can write 90 degree, and then E ds cos angle is how much? 0 degree bete. So 0 degree. This is our second surface, and then E ds cos 90 degree. Here you can see. So here this is for third surface. You all know that cos 90 is equal to 0. So we will not have any value of this, and we will not have any value of this. In your board exam, when you are preparing this question, no need to cut in this manner as I have done it. I have done it just to tell you that this value is 0 and this value have something, but this value is also 0. Now, see, if I will write electric flux now, then electric flux equals to this value 0. So this value have some value. You can take E outside, ds inside, and surface area, and that is equal to 2 pi RL, because we know that the surface area of cylinder is 2 pi RL. How? This is what? Length that we have taken, maybe L, and this is what? Circumference of the face. So 2 pi RL of the circumference, and the length is L. That you already know, you have done in your previous classes. So this is 2 pi RL, and then it is what? 0. This is due to second surface, and rest of the surface electric flux is 0. So from this expression, we understand that the total electric flux due to an infinitely long straight wire is due to only second surface, being the first surface and third surface, they are not contributing in total electric flux. So here, next step is phi E equals to E. We have already done in our 11th class, the integral of ds is S, and we will put here the direct value of S, and that is what? 2 pi RL. So here we can write 2 pi RL. This is the equation number 1. Now, according to Gauss theorem, I think you all remember what is Gauss theorem. So that I am writing here directly that electric flux equals to charge upon 1 upon epsilon naught. This is also flux, this is also flux. So we will equate both the values, both the equation we have to equate. So we can write here on equating equation number 1 and equation number 2. So when we will equate equation number 1 and equation number 2, then we can write E into 2 pi RL and equals to charge upon epsilon naught. And then the value of E equals to Q upon 2 pi RL into epsilon naught. Basically, this is our formula. But in 12th class, we will not find our formula in this manner. We will find our formula in the form of surface charge density, or you can say linear charge density, or you can say volume charge density. So what are these densities? So here, we require linear charge density. So I think you have heard this term first time. So just remember, what was the expression for the mass density? What was the formula for that? The mass density formula was mass upon volume. But here I told you linear charge density. So I am telling you what is the expression for it. So here we know that charge density, linear charge density, that is represented by lambda, and the formula is total charge upon total length. Let the total charge present on this infinitely long straight wire is equals to Q, and the length we have taken already L. So what is the expression for the linear charge density? Lambda is equal to charge upon total length. So here, if we want to find out the value of Q, that is equal to lambda into L. Now put the value of Q here. When you will put the value of Q here, then the expression for the electric field becomes lambda L upon 2 pi R L epsilon naught. You will cancel out L with L. And then the expression for the electric field equals to lambda upon 2 pi epsilon naught into R. And this is the expression for the electric field at distance R due to infinitely long straight charge carrying wire. This was all about related with my first application of Gauss theorem. In another module we will discuss another applications of Gauss theorem. Thank you.